Here we come. Okay, so um, today I am going to try to read along and try to finish this exercise. Um, so I got this Pytorch um, scholarship from Facebook. This is, I think, is from part. So I'm doing now lesson 4, which is still Introduction to Pytorch on the network architectures. So this is one of the uh, how do you call it, exercises that are still kind of easy to follow if you are just getting started with the PyTorch, which I am. I'm just a beginner. The nice thing about PyTorch is it's very if you know already about Python, then it's kind of easy to follow along. All right, here we come. So neural networks, right? So we are here at the losses in PyTorch, basically defining how do you calculate the loss, basically. So you pass through this data through your neural networks, through your linear transformation neural networks, and then you're gonna at the end of the output, right? Um, you're gonna calculate the the um, the error, right? And then the error is basically is where you are, um, and then you're gonna compare that error to the ground truth data, yeah, the label. We're talking about supervised learning, right? So once you know how much is the error, and then you're gonna do a gradient descent, basically. Basically, is a general calculus calculation. You basically compute the derivative of that error with regards to the all the weights, right? Um, but in order to compute the error, uh, there are several algorithms to compute the error. So remember, the error is basically the output that you get from the linear transformation of your neural network. You are basically comparing with the ground truth. That's the error. But it's not just as easy as just the y output minus the y label. It's a bit more complicated than that. So let's see here. So in PyTorch, there's this thing called NN model, right? It's basically like a library, and inside that library, there are several losses algorithm. One of them is cross entropy loss, which you can call it using that on NN dot cross entropy loss. You usually see the loss assigned to the criterion. Um, as noted in the last part, with a classification problem such as MNIST. MNIST is a classification problem to basically, I think, is classify handwritten digits. Okay, we are using the softmax function to predict class probabilities as the final layer of the output. Um, because it's a multi-class. If it's just one binary class, you don't have to use softmax. You can just use something like I think sigmoid or so anyway. So with the softmax output, you want to use cross entropy as the loss. Okay. So if you use a softmax output, which is a multi-class probabilities, between 0 and 1. So in this case, you're trying to detect the handwritten digits, and then the output will be whether it's a 10 class probabilities from you're trying to predict from 0 to 9, and then it will give you probabilities, what are the handwritten digits of the input. In this case, it's 4 is the highest probability, and then 9, and the rest are kind of like 0 here, as you can see, right? And then all the sum of all these probabilities are is 1 basically. So and okay, anyway, let's go back to here. I'm a bit lost. Okay, so once you have the softmax as the output, you want to use that to compare it to the ground truth, right? Because as in the first forward pass, your weight and your biases has not been um, uh, uh, adjusted yet, or has not learned yet, right? So you want to compute the gradient, but in order to compute the gradient, you need to compute the loss. So and this one is basically the output of the softmax. You put it on the cross entropy. To actually calculate the loss, you first define the criterion, then pass in the output of your network and correct labels. Okay, so there's a documentation here. Use cross-entropy loss. This gradient combines NN, log softmax, and NN allows in one single class. The input is expected to contain score for each class. This means we need to pass in the raw output of our network into the loss, not the output of the softmax function. So you need to pass the raw output of our network. Oh, not the output of the softmax. Okay, because the cross-entropy loss is already combining, um, is already the the softmax is already embedded inside this library. Okay, so you don't have to pass it through the softmax function anymore. Okay, this raw output is usually called the logits or scores. Okay, we use the logits because softmax gives you probabilities which will often be very close to 0 or 1, but floating point numbers can accurately represent values near 0 or 1. It's usually best to avoid doing calculation with probabilities. Typically, we use log probabilities. Okay. Okay, is this kind of confusing? Okay, anyway. So what we're doing here is I'm using Google Colab. By the way, if you are wondering what I'm using, it's free. So this is the first thing I do, just install Torch, exclamation mark pip install Torch, and then I'm importing the necessary um, module or libraries. So I'm importing the NN, the neural network modules from Torch, and then I'm importing functions, which is basically is a library of the activation functions, as far as I know, like sigmoid, softmax, and all that stuff. It could be crescent entropies also here. Um, and then importing also the torch vision, uh, which is neural network torch for vision stuff. So like vision stuff is for like I think convolution net and all that stuff, right? The good stuff, which is basically designed for vision. Um, and then define a transform to normalize the data. So what we do here, um, okay, so we have transform.normalize 0.5, transform compose. I'm not sure about this. Yeah, and then load the training data. Yeah, I think this wouldn't work because there's a touch vision. I think I have to import it over here to install. I mean, that's it. Yeah. So module not found error, touch vision. So we have to install that too. That install torch vision because it apparently is a separate library or separate package. Okay, now it's done. Now we can run this one, right? Okay, so we have basically we're putting the MNIST data from the Pytorch. Um, we are putting it into the train set. We're going to data sets at MNIST, and then on the train set itself, we just take 64 because we were just using for exercise purposes. We don't want to train the whole thing. I think MNIST there's like I don't know like 50 or 60,000 something like that. Yeah, it's a lot. So we're just taking 64 images, shuffled through. I think it's just to make it randomized. Um, how it takes these 64 images, and then you're evoking the torch library from .utils.data is a data loader. So you're putting it into the data. Okay. So, oh, what did I do? I have no idea. Oh, okay. Okay. What is this? Oh, okay. Anyway, I think I just downloaded by accident. Um, okay. So if you want to see what it looks like, um, what is the train set? We can just see. Okay, so it's just an object with the data set is MNIST with a number of 60,000 and and then the root location and the transform to normalize it. I think this is just to normalize the images into 0 and 1, right? Um, so that's the train set, and then you can take a look at the train loader. It's just 64 images. It's an object. Okay, I think you can call this. Let me see. Can you just call like the first image? Nope. Can you call the shape? No. Okay. Whatever. So it's just an object. What? Oh, okay. The bed size. Okay. 64. Okay. 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 So this is where we are building the sec the end of the part two notebook. Is this part two? I don't know whether it is part two. It's kind of confusing. So anyway, okay. So we're defining a neural network here, the feedforward network. So we are just taking the nn.sequential library and then parentheses. So and the first, this is like the first layer because we are trying to build. There's no pictures here. Dang it. Okay. Anyway, okay. I'm trying to describe it using my mouth. Hopefully you understand. So what is it's doing over here basically is taking a 784 um, images. Sorry, 784 data points, which is the factor of our images, right? Our images is it's basically as 28 by 28. So imagine 28 by 28 pixel for every image, and then we just grabbing 64 of them. We're gonna train 64 of them, right? Um, let me see. But let me see if I can. How do I like? Oh, pet sampler. Huh? There's a pet sampler. Trying to see if I can see the pet size, data set, number of data points, split train. Okay. Anyway, anyway. Okay. Let's just move on. Okay. So over here is we're defining the first layer of our neural network, which is the from taking is a linear lane layer. Okay. Linear layer is just or linear neurons just means it's not it doesn't have a feedback. So it's just an ordinary neuron. It's just imagine a neurons taking linear transformation, just taking the inputs, multiplying by the weights, and add the bias. So that's what a linear is. Okay, there's no like fancy stuff going on after that, right? It's just a simple linear transformation. Just remember your high school algebra is y equals to mx plus b, right? So it's taking basically 784 inputs as a vector. Um, this is defined by 28 by 28. So 28 times 28 is the how big is our images. For every individual images is basically is a square image. Let's see, 28 times 28. Oh, that's cool. 784, right? So it's taking 784 vector inputs, yeah, and then it's gonna spit out 128s. How do you define 128s? Basically, it's this is the job of you want to be like serious into this deep learning, like a researcher or engineer. This is kind of your job. After some time, you get an intuition of like what are the numbers should be, right? Whether it's 128 or 64 or it's like 312 or whatever, right? Um, but to give you a rule of thumb, if you have, so basically the input is 784, and then you just want to classify, it's a multi-class classification problem. So you are trying to classify from 0 to 9, right? So there are 10 classification, right? It's a handwritten digits, right? Whether it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So anywhere in between kind of is for me. I've been I don't know. I've been learning this for about 6 months or so. Um, it has to be, I think, has to be like in between this one, and then it seems to be the neuron also has to be like an even number, right? Right. So that's kind of like really, really, really like a rule of thumb. But you kind of do like a trial and error basically. Right. So anyway, so this is the first linear transformation, right? From the input to the first hidden layer. So there's at least one hidden layer, and then from the hidden layer we are uh, uh, from that output, um, uh, we are basically gonna fit it into the nonlinear activation unit, basically a ReLU, right? Um, so let me see. Is what F. Sorry, actually, you don't have to do this anyway. As fast F. Okay, because you can just call the ReLU like that. This is nice actually. Okay. Anyway, so after ReLU, you're gonna pass into your second linear second layer, which is also a hidden layer, right? Um, uh, so this is already like the second hidden layer. This is like the first hidden layer from 784 to 128, right? And then the second hidden layer from 128 to 64, again, is a linear transformation, right? There's nothing fancy here. We're just using the standard linear neurons, uh, which is basically multiplying the inputs by the weights and plus the biases, right? And then we also output with an activation function of ReLU. ReLU is one of the most popular, most common, and I think is kind of, from my understanding, is the one that works uh, across general, like where you know, the one that wide use cases. Um, and then after the second hidden unit, you want to connect it to the last layer, which is the output. So you want to connect all the 64, which is the 64 here. Yeah. So if you notice here, the input, I mean the output of the previous layer, it becomes the input of the successive layer. And so it's this 64 output, it becomes the input of this output layer of the linear neurons, right? And then the output is just 10 because we are just trying to predict the 10, what are the most likely 10 handwritten digits of between 0 to 9. Okay. And what we are defining the loss here over here. So we call again the NN model, and then we just dot cross entropy underscore, sorry, parenthesis and loss. We normally we use criterion, but you can use something else. You can use like just like loss or something. It doesn't matter. Um, and this is where we get our data. So our all our data is already in a train loader. We can iterate it, okay, it's with the iteration function, and then we can call the next function, and then this is just gonna keep on iterating like from the first until the last images, and I'm just gonna put that into two output basically. One is the images, and one is the label, right? So if you I think if you take a look at this, it's gonna the if you what are the images? It's basically all of the vectors, or basically the pixels of all the 64 images, right? And and this one is the label, whether that's between 0 or 9, basically all of the respective 64 images, right? And over here, we're gonna flat the images because remember, our images is still in matrix format, which is 28 by 28, and we want to put it into a one dimension of vector representation, which is 784 inputs, uh, uh, unit factors here, right? So what you want to do is uh, basically you want to flatten it, but yeah, there's this convoluted kind of function that you have to call. Basically, you call the images dot shape, and then you want to, I think, underscore parenthesis 0 is basically the um, um, I don't know what it is it mean 0. That's a good question. I know this one means -1 is it means the dimension has to be reduced by 1, right? I'm not sure about this shape 0. Um, Probably we can take a look at that. Yeah, um, definitely. Let me, uh, okay. Anyway, so and then once we flatten the images, we want to call the model function. The model function is basically this is our model, and then we put that all of the images and um, into the model, and then the output is we call it logits. Basically, it's because it's a non-probability, it's just a number, right? And it could be more than one. And then we want to calculate the loss function, right? So we call a criterion, which is basically using the cross entropy loss, and then we want to compare the logits with the labels over here. Okay, so this is it. Let's run this. Let's run this one. So you got the loss of 2.3, right? Uh, I want to test this one, images.shape0. Um, how about if I print images.shape? So it's 64 by 784. Okay. If you print it over here before you flatten it, so you got the idea what does the the flatten function does. So if you can see, uh, before it got flattened, this is the like the the shape of uh, the image. So it has 64 images, and it has, I think one is one channel. I think one, like, yeah, one channel, because it's a it's grayscale image. I think if it's a color, it's going to be three, because it has three channel, R, G, and B, red, green, and blue. And then this is the factor is 28 by 28. It's a square images. But once you go through here, this flattened thing is going to be only 64 by 784. So 64 images, and each of those has 784 uh, one-dimensional factor representations, right? Um, uh, and I just want to show you what does it look like if let's say if I print images, um, probably I can print it over here. Images, images, shape. I think zero, shape zero is this guy. I think that's shape zero. It's 64. I think, yeah, it's 64. The shape one is the one, yeah, and then until two, three. So four, it should be nothing, yeah, out of range, right? So zero is the 64. So what does what? So I think I understand what is it mean. So images.shape.0 is basically it's taking the shape of the that images at the zero index, which is the 64. So basically, this is just 64, putting it over here, because you still want to keep that, but at the same time, you also want to reduce the dimension by one. So this is the two dimension. You want to reduce it into -1, so it's just one. And then what this view function does is automatically compute what does it take if you want to reduce this 28 by 28 into just one dimension, which is so it is going to compute automatically to 784, right? So you don't have to do that thing, right? So you just specify -1, but you still have to specify you still want to keep the shape of 64, right? Uh, because if you want to, let's say, get the shape of one, then it wouldn't. It's gonna mess up. I think it's not gonna compute properly. Yeah, there's a runtime error, because if you take one, that means it's gonna take this is just gonna be one, because that's the grayscale channel. And so it's gonna be one. The torch size is like one over this guy. Oh, okay, that's weird. Anyway, it's just messed up. Okay, I don't want to deal with that now. Okay, okay. So anyway, So that's good. Why is not printing? No, no. Oh, yeah, here. Okay, so we're here. So it's saying here, in my experience, it's more convenient to build a model with a log softmax output using nn.logsoftmax or f.logsoftmax. Then you can get the actual probabilities by taking the exponential, which is torch.exp, and output. With a log softmax output, you want to use the negative log likelihood, nn.nll/documentation. Okay. So now here I am trying to we'll see what happened. Okay, so the exercise is we're trying to build a model um, that returns the log softmax. Okay, so as the output instead of softmax, and calculate the loss using the negative log likelihood loss. So you want to use this, right? Okay. Wait a minute. I thought they said if you use cross entropy, you don't have to define the oh, okay, because it's linear. Oh yeah, yeah. You don't have to define the because in cross entropy loss, um, the um, the activation layer is already inside here, which is using I think softmax, if I'm not mistaken. It says here somewhere cross entropy where is it? So this criterion combines and unlocks softmax and in one single class. With the softmax output, you want to use cross entropy. Okay, 3 and Pytorch provide losses such as the cross entropy loss. See the loss as underrated as nothing less. With the class we're using softmax functions to break class. With the sum example, you want to use as the loss. So actually calculate the loss, you first define the current, then pass in the output of the current labels. Something really important in looking at that. This criterion combines an hand and in one single class. Okay. Um, okay. Okay. So now we are going to. Okay. So wait. Hold on. Build a model that returns the log softmax as the output and calculate the loss using the negative log. Okay. Note that for nn dot log softmax and f, you'll need to set the dim keyword argument appropriately. Dim equals 0, calculate the softmax across the rows. So, okay, calculate softmax across the rows. So each column sums to 1, while you calculate across the column. So each row sums to 1. Think about what you want the output to be. So you have to use dim1 because that's a softmax function does. It basically um, sum up all the exponent of the vectors across across the row. Sorry, across the column. Across the column. Yeah. So each row sums to 1. Yeah. Yeah. Because what you're gonna have is you're gonna have 64 rows by at the output, okay? 64 rows because you have 64 images, right? So each of those rows represents each of the image, and so 64 by 10, right? So 64 rows by 10 column, and each of the column represents basically the probability or the logits of each what class is that going to be if it's from 0 to 9. Yeah. So what you want is you use dimension equals to 1 because you want to calculate across the column, right? You don't want to calculate across the row. If dimension equals 0, you calculate softmax across the row. No, you don't want to do that. Okay. So the model, okay. Let's see this. So you use nn dot sequential. Let's see if it works. And then we just follow this. Okay. Okay. So the first, wait, what are we building again? Oh, okay. So we're basically the same. I just want to compute this. Okay. So first we have the linear model, which is I think 784, and then the output is 128, I think. Correct? Okay. And then the next one is also uh, linear model. Let's make it the same. We pass it through the ReLU function. Okay. And the second hidden layer is also linear. We're gonna take that as an input, the output as an input, and then pass it to 64 vector output. And then we are passing that to the ReLU function again. Okay, and then the last layer, we're gonna build another linear model. Again, it's always linear in this case. Because it's just a linear transformation. It's 64, and then you pass it into 10 multi-class logits. Okay, I think that's it. Yeah, yeah. And then you define the loss. You want to use negative. So you're using the negative log likelihood loss. So it's nn dot n ll loss. Okay, so nn dot n ll loss. This is the function that you want to use. Um, I think you have to pass in the model, right? No, wait, just like that. I think, yeah, yeah, okay. And then you get the data, the same thing. And then you get the logits from the images after you flatten it. And then you compute the loss, comparing the logits and the criterion, the label. Sorry, the logits which you get from using that one. Okay. So I think you have to use nn.log softmax here. I don't know. Let's print this one. There's no attribute ReLU. Really? Okay. I think I got it wrong. Oh, oh. Okay, this is why you need to actually code this, because when you read it, you understand it, but when it comes to coding, you make a lot of mistakes. So you just have to do it. Right. Okay, so you have the tensor point 0.05. I think this one is not the one that um, the exercise is looking for. So this one, the tensor is 2.3. I'm just gonna wait. I'm just gonna um, like unmark this so it's more concise. Cross entropy, cross entropy loss. Okay, I think I have to use sorry, I think I have to use NN uh, log softmax, the last layer. It does seem to asking me to use it, so error. Okay. Mm, interesting. I don't know why it's an error. Oh, I think I know, because I didn't specify comma here, right? I think so. Nope. What's that? Implicit. Oh, oh, you have to. Okay, okay. Okay. Yeah. Okay. Okay. Dimension equals one. Okay. I think that's about it. So the tensor now is 2.3. Almost the same. Yeah. Okay. Um, let's see here. This criterion combines in one single class. Documentation and the cross. Okay. Torch and then cross entropy loss. Um, okay. What does it mean? Um, does it mean that the weight, size average, ignore index, reduce? Okay, so input cross entropy, cross target. Um, and then logs of max. Okay. So loss equals to data input, data torch and another conf torch empty torch loss. I don't know what does it mean. This created and combines into one single class. It's just to enter in class. You can okay, it should be one. So when you have an unbalanced training set, the input is expected to contain score for its class. Input has to be assessed. The answer. Okay. Um. Yeah, I don't know. Let me let me think about it. This. The first exercise is wait. Okay, there's no. It's just restaurant entropy loss, right? Okay. I think this is correct. I think. Okay, let's see the. I think this one, right? Yeah. Yeah. So it's defining the nn dot log softmax and dimension equals to one. Yeah. So I was correct. Yay! So I was correct. Okay. All right. Thank you guys for listening. That's about it.